The title is Where Physics Still Doesn't Work. I should probably say particle physics. The global quest to solve the universe's enduring mysteries. And I'll introduce the speakers, panelists, and then ask a few questions and open up, hope you'll ask questions. This is Fabiola Gianotti. She's Director General of CERN since 2016. She's been at CERN since 1987 when she arrived as a graduate student at the University of Milan. And as spokesperson for the Atlas experiment in 2012, she made the announcement of the discovery of the Higgs boson, which I think even before that, but that especially propelled her to public recognition, and she was on the cover of Time and listed as one of the top most influential women by Forbes and as a leading global thinker by Foreign Policy, and listed as one of the top most inspirational women by The Guardian in the UK and so forth. So, and besides that, she still continues to do physics in addition to leading the premier particle physics lab. At the other end, well, next is Renaud Pin. He's the director of the French National Institute of the Nuclear and Particle Physics at CNRS since 2015, and the research there spans particle physics, nuclear physics, accelerator development, instrumentation, medical applications, grids and cloud computing, and more than that. He started off in theoretical physics and worked at DAISY and CERN, and later got involved in observational cosmology. Has been involved in the Large Synoptic Survey Telescope, an international project that's being built in Chile, and in the Supernova Cosmology Project, and his work has focused largely on neutrinos and supernova and dark energy. And then Laura Baudi is a professor at the University of Zurich, and she specializes in astroparticle physics. She's the spokesperson for the International Darwin Project, a 50-ton liquid xenon dark matter detector, expected to start collecting data in 2026 at the Gran Sasso National Laboratory in Italy. She chairs the Xenon Collaboration Board, which is a deep underground experiment at LNGS for dark matter research, and the Science Advisory Committee of the European Astroparticle Physics Strategy. And then Nigel Lockyer is the head of Fermilab, the US flagship particle physics lab, which is located in Batavia, Illinois, and he's been there since 2013. Before that, he was head of the Canadian Particle Accelerator Lab Triumph in Vancouver. And Fermilab's main focus these days is on neutrinos. And the lab is building and hosting the Deep Underground Neutrino Experiment, acronym is DUNE, which is a major international collaboration bringing together scientists from 31 countries, and it's the first truly international project on US soil. A long time ago, he told me that he was going to leave physics to go into business, and then a physics professor told him, physics is more fun, you won't earn as much money, but stay in physics. And he obviously came a long way with this. So I want to start by asking each of the panelists to say what you think are sort of the most inspiring, important, interesting questions in the field at the moment. There's mics there. Yeah, whoever wants to start.
So I can start perhaps. So this is actually a very exciting and very interesting moment in fundamental physics, because we have understand a lot of how the fundamental constituent of matter works and how the universe works, but at the same time is a moment where we have a certain number of open questions for which we have absolutely no clue. The theory that we know today doesn't help us much. So it's really, in some sense, uncharted territory. So there are many questions. The first one is perhaps related to what we call the dark universe. So today we only know 5% of the universe, meaning that when we in the night we look at the sky and we see the nice stars, planets, galaxies. What we see is only 5% of what is out there, and the rest is made of form of matter and energy that we don't know. So for this reason we call them dark matter and dark energy. Actually the term dark indicates at the same time our ignorance and the fact that these form of matters and energy do not interact directly with our instruments. So we deduce their existence from indirect proofs. And now today, based on cosmology and many experimental evidence and precise measurements, we know that dark matter is about 25% of the universe, and the dark energy about 70% of it. And there are many other questions. The asymmetry between matter and antimatter. Why today's universe is almost exclusively made of matter. We thought that when the universe had origin, about 13.7 billion years ago, matter and antimatter were present in the same amount. And then at some point, nature has decided antimatter will disappear and only matter will survive, which is also why we are here, because if matter and antimatter were in the same proportion, we will not exist, because they annihilate with each other. Now, I would like to stress that antimatter is as nice and as beautiful as matter, in spite of the fact that several movies or books depict it as dangerous or whatever. At CERN, we produce it. We have the only dedicated facility on the planet to produce antimatter. It's called antiproton decelerator. We produce antiprotons, and then together with anti-electrons, we synthesize anti-hydrogen, and through this process, we are able then to measure anti-hydrogen and compare it with hydrogen and see if there is any tiny difference which could help us understand why antimatter at some point disappear. Neutrinos, but I guess that my friend Nigel will mention it. Neutrinos are very mysterious and elusive particles, and there are many sexy questions related to neutrinos. I think I will stop there so that my colleagues can take over.
Yes, so one thing which I think have been, always in my mind as a scientist or as a student is this question of vacuum energy, actually. So Fabiola mentioned particle physics. She also mentioned the acceleration of the expansion of the universe. She didn't say acceleration of the expansion, but let's say the universe. And I think it's amazing to think that those are very much related, as a matter of fact. And one of the connection is the vacuum. Particle physicists think of the vacuum as being full of particles and antiparticles pairs who annihilate, that you can even extract from the vacuum. And the universe is accelerating currently. The expansion is accelerating, probably due to some presence of some dark energy, which could be somehow related to the vacuum energy. And I think this is a really interesting question that physics has to address today. And with all these experiments at CERN, or even large telescopes, or space experiment as well, we are all working toward understanding this vacuum energy.
I can use it. Okay, so maybe I'll try to perhaps elaborate a little bit on two of the questions that Fabiola mentioned. So one being this matter-antimatter asymmetry and neutrinos, because there might be a connection there. So and maybe you know that neutrinos are the only elementary fermions in the standard model that are not charged. So in their case, we can't say whether they are their own antiparticles or not. For all the other, like electrons or protons, neutrons, and so on, we know about the antiparticle. But in the case of neutrinos, this is still a pretty much open question. And why is it so interesting? So neutrinos are neutral. They interact only via this, what we call the weak interaction, so very, very weakly compared to the other fermions in the standard model. And this question, might be connected also why they are so much lighter than all these other particles. And by the way, we know that neutrinos are not actually massless as predicted by the simplest version of the standard model. But one question where we don't have the answer yet is what is the mass of these neutrinos. You know, we know it's many orders of magnitude lower than for these charged fermions, but why is it so much smaller? So this is one of the intriguing questions. Fabiola said neutrinos are these elusive, these very mysterious particles, and they might also have, you know, give us some clues about what's happening at much, much higher energy scales, you know, because the smallness of their mass might be connected to things that happen very early in the universe. So this is one of the questions I find intriguing, and you know, there are many others, but maybe also to elaborate on this dark matter. Again, as Fabiola said, we have this indirect evidence only due to its gravitational interaction with matter so far, right? So from very early, from the early universe via this cosmic microwave background to this, what we call the large-scale structures in the universe. So structures that are at the scales of galaxies and larger than galaxies, galaxy clusters, and larger structures like these voids in between. So we know from their counts, from the distributions, from the movement of objects in these clusters or in galaxies, we know that there is this so-called invisible matter that sort of glues everything together. And the simplest explanation actually is it's made of a new particle. So this simple explanation, you know, could be more than one particle, of course, but the simplest is that it's one new particle, and that can explain everything. But the big mystery is, what is this particle, and why haven't we seen it yet? We are looking for it. At least personally, I'm looking for it for 20 years now, a bit more than 20 years. And you know, we might never know, but it's something that it's a big challenge. So.
All right, so maybe I should talk about the Higgs boson then. So I think the interesting question our field has, we've discovered the Higgs boson. It's a unique particle. It's the only particle with certain properties in the standard model. It's if you think of it as a field, it permeates the entire universe. And now the question is it what we think it is, which is what the Nobel Prize was given for, or is it something different? And I think most people think it's something different. And so the fact that it's a particle, fundamental particle without spin, is a really big deal for particle theorists, because almost every extension we talk about in terms of new theories, extra dimensions, inflationary universe, all these kind of things you've heard about, all involve particles with properties like the Higgs. So now that we've discovered the Higgs, there's you know, sort of a general rule that nature knows how to reproduce itself, and so we expect to find these other particles. And the question is, where are they? What is their mass? Do we look for them in cosmic rays? Do we build big new accelerators to find them? But there's definitely a sense that there's a lot of physics out there that we haven't found, which is very, very exotic. It ranges from what happens at 10 to the minus 34 seconds in the universe to what's going on in the intricacies of quantum physics. It's somehow all connected, and we haven't made that connection yet. So I think what the field of physics does now is discuss, given finite number of people and resources and so on, what is the right direction to proceed? And the planning for that throughout the world is just being initiated here in Europe, and it will continue in the U.S. and Asia in the next couple of years.
Definitely get back to that kind of planning, but I'm wondering, can you say something about how these different things that you've mentioned, the antimatter and matter and neutrinos and dark energy, vacuum energy, dark matter, all these things, how finding some of them may help you understand the others? How are those questions interconnected?
Well, the questions are interconnected because we think that the underlying physics is the same. So, for instance, discovering new forces, new sources of energy in terms of forces may have an impact on our understanding of dark energy. Understanding how neutrino behaves will give us hints and on the matter-antimatter asymmetry in the universe. Same for the Higgs boson. So there is a strong correlation. The underlying physics is the same, and every single step forward that we make in answering one of these questions. And of course, you understand by the by the importance of the question, what a great discovery will be just to answer one of them. It will be absolutely amazing. But this discovery will tell us a lot about the other questions. And this is why also we are trying, because the questions are so important, they require different instruments, they require big and complex instruments, they require the community of scientists, engineers, physicists, technicians. That's why particle physics is a global discipline now. So we try to optimize the facility globally. So for instance, the US has now taken a leadership role in neutrino physics together with Japan. We are not going to build a neutrino facility at CERN. We are working on neutrino detectors to collaborate with our US and Japanese colleagues. Similarly, in Europe, we have a little bit the leadership of what we call the energy frontier, so high energy colliders, and so our colleagues from the US work with us. In Asia, there is a little bit of competition. We'll discuss this perhaps later on. But the idea is not to replicate 2 times or 3 times the same facility, exactly because of this interconnection of the various questions, and because of the complexity and the challenges that addressing the question require also from the practical, financial and technical viewpoint.
I can say my favorite example of where they're connected. So I mentioned the Higgs boson, which the Nobel Prize was given to the Higgs because people believe it gives mass to the fundamental particles. There's a large number of theorists, I would say, that think that the mass associated with neutrinos is not given by the Higgs boson, that there's a different type of mass in the universe that is called Majorana mass, which was invented by a brilliant young Italian physicist who is a book in itself to talk about his life. But Majorana invented this type of mass which has not been observed, which is very different from what we know today. It could be the neutrino mass, but it could also be dark matter as well. So once you have an idea, you ask yourself, does this idea fit into any of the holes we have in our thinking? And so that's one way it's connected. So neutrinos and dark matter may be connected in that way.
So what do you do when you have all these open questions and you know sort of what you don't know, but how do you know where to look for it?
Well, so, we heard of a few open questions, right? And obviously not everybody can look everywhere at the same time. So that's why I think we have instruments to look in specific regions. Also, just taking dark matter as an example, I mentioned that it could be a new particle, but theoretically speaking, that particle is not too well defined. There are some leading candidates where we know the sort of what the mass would be of that particle and how strongly it would interact, or how feebly, I should say, it interacts with the rest of the matter. But that parameter space is pretty vast, so we are trying to cover much of it, from looking, let's say, for very, very light particles to pretty heavy particles, like maybe 1,000 times the mass of a proton of a hydrogen atom, for example. Or so, and for this we have to build different type of experiments, right? We have some theoretical guidance, but again, given that we haven't seen anything, at least in our type of detectors in the last decades, we have to sort of expand these searches. So we don't know very precisely where to look for, but we have some ideas, and then we are trying to improve, to improve what we call the sensitivity, to probe ever lower and lower interaction probabilities of this particle with a normal matter, because there's some theoretical prejudice that they might interact apart from just gravitationally. It could also be the case in which case we can't make them in the lab, in which case we can't see them in what we call our type of direct detection detectors, where we just look for these particles that are in the halo of our galaxy to scatter off atomic nuclei in a detector, right? But if this, on the other hand, if this what we say dark matter particles were there in the early universe, and if they had some interaction apart from gravitational interaction with the rest of the matter, then at some point we should be able to see that.
Yeah. Maybe I should add that in terms of choosing where to search for something, there is a practical aspect of what we can achieve in a lifetime or even a shorter time. Technically, I mean speaking, so we have to build instruments, and we are building instruments that are very complicated, very state-of-the-art, and of course this requires means, but also being able to do it. I mean, if we try to reach something which is so high energy that we won't be able to build a machine, there is no point in doing that. So this is something we cope with every day. We have to build instruments. It's experimental physics. We want to find new things. There are plenty of possibilities, and we find our way.
This might be a good time to open up for the audience to ask questions, and I think there are mics in the aisles. I don't know if there's people also running around with them, but if people have questions, please come and ask them, introduce yourself and ask questions, and otherwise I can obviously continue asking questions, but I hope we can get a discussion going.
Can you hear me? No. Okay. Thank you for this nice panel. I'm Dr. Saray from Gazi University, Ankara, Turkey. I do multidisciplinary academic research on science communication. My question is, please correct me if I have heard wrong or misunderstood. There was a topic about discovering of something what you don't know. I just had the idea of reminding the audience the periodic table. There was a philosophical approach and a systematic thought, and the periodic table was prepared, but there were elements not known. And the physicists or the other relevant scientists have worked on it to find out what is not known, but what has to be there. So I would like to hear from the esteemed panelist if there is any philosophical thought or systematic approach to the particle physics that there has to be, like periodic table, something is there, but can be found not only through precise instruments, but with the human thought as well. Thank you.
Okay. Go ahead.
Well, I think, okay, I will start, but I think this is a very, very good example because I think there's also 150 years this year of the celebration of the periodic table of the elements. And Mendeleev, it took him a long time. He knew quite a lot of the elements, but it took him a long time to find, to put him in this order that we sort of know today, and to realize that there are patterns, and from those patterns to infer that there must be additional elements, right? So this is what you can do by pure thought, but then you have to go and actually find those elements, demonstrate that they're there. For example, I work with noble gases, and those noble elements like argon, krypton, xenon, and so on, those were really latecomers, and some of them were in fact discovered by Ramsay in the UK. He also got a Nobel Prize for it. And now to go to particle physics, we also see patterns there. We see, as probably many of you know, that these elementary particles, they come in three families. The so-called leptons and quarks, and we do not know why exactly three families. And there's, the question: could there be a heavier family? Could there be a fourth one? At this point, we don't know. You can look for it. You have some constraints from existing data, from existing experiments. So yes, on pure thought, you can ask yourself, what's the reason why there are only three families, right? But again, you need detectors, you need experiments to find out whether is there a fourth family of a much heavier sort of maybe leptons and quarks that we haven't seen yet, and so on.
Yes, I can complement what Laura just said. I think the answer to your question is yes and no. Yes, in the sense that the history of particle physics shows that there have been the period where the standard model of particle physics, the theory that described the elementary particles and their interaction, those that we know and we have observed, was developed, that had been foreseeing certain number of particles with the pattern of families that Laura explained, and we knew at some point that some of those particles should be there, and the experiment have been discovering this particle one by one. So for instance, when the top quark was discovered at Fermilab in 1995, it was not, it was predicted, it was, we could just on the basis of thought think that there will be a heavy fermion, and that was actually at the end it was discovered. Today we are in a different situation. Today the standard model that has been our guidance, theoretical guidance for decades now, is complete in the sense that has been completed in the sense that all the particles predicted by the standard model have been observed, but at the same time we know that the standard model is not a complete theory, because the standard model cannot explain neutrino masses, cannot explain dark matter, cannot explain dark energy, cannot explain why the Higgs boson is so light. And so in this moment we are in a situation where there are many different roads open, and it's not just completing some kind of pattern that has been taught and developed by theories, but it's also exploring uncharted territory.
Thank you.
Okay, so Yun Yu from Insa Science. So my background is not in particle physics, so perhaps I have a rather naive understanding of some of these topics, but I've been trying to understand supersymmetry, the theory of supersymmetry, and I've read blog posts that talks about how the theory is dead, because we've already looked in the areas where particles are predicted by supersymmetry in order to solve the hierarchy problem, and particles are not there. So there's like a certain percentage of the community that declare the theory to be kind of a moot point. So I just want to see what's everybody's perspective on that, and then related to that, there's also, of course, in China, this huge discussion a couple of years ago about this proposal of building the next huge particle accelerators, and people are saying if we don't know exactly what we're looking for, like we did for the Higgs boson when we built the accelerator in Europe, we should not invest such a huge money to explore just for exploration's sake. So I also want to get the perspective on that as well. Thank you.
Maybe I take the question on supersymmetry. The way to think of it is that we know there are two kinds of particles, which we call fermions for one side and bosons on the other side. And this supersymmetric theory is somehow a way to unify this vision of two kinds of particles. They come from the same object, or different vision of the same object. So that's a guiding force, I mean, simply speaking. But it's also very much motivated by theoretical, thought on symmetries. And so that's the basic of the reasoning, searching for unification and theoretically motivated theory. Now, once you've said that, you haven't described the word, a possible word. I mean, there are many possible implementation or description of supersymmetry. And what you've been describing and hearing is the fact that the simplest model for supersymmetry is probably doesn't work, doesn't describe reality. And therefore people are looking for, not as simple models, some more complicated model, maybe some more elaborate models for this theory to apply. So it's not totally dead. It's the simplest version of it. People like to say that it's probably not working, but that's where we are. And it's certainly this quest for unification, in a way or another, is really a driving force. Coming back to the first question, it's really almost a philosophical driving force for doing this search. I don't know, for the other question I can leave.
Okay, can I reply? Perhaps I can reply to the other question. So there are two regions of the world at the moment that are, well, there are actually three countries or regions that plan to build future colliders. So Japan is interested in building a linear collider and a plus and minus collider. China, on the other hand, is interested in building a circular collider, 100-kilometer ring for electron-positron and subsequently proton-proton collisions. And CERN at the moment is discussing whether we want to build an E plus and minus linear collider, so-called CLIC, or a circular collider similar to the one in China, a 100-kilometer ring. So already the fact that there are three powerful regions of countries interested in these big machines indicates their interest, A, for science, and B, for technology and for society. Second, yes, they're expensive. However, this is not money that you put in the table in a couple of years. It's money that is spent over decades. And third, it's true that we were in a lucky situation when we built the LHC, because we knew that either the Higgs boson is there or the theory becomes some sort of crazy at the energy scale that the LHC will explore. So something should be there. Today, we are not in as a comfortable and nice situation. However, research is the investigation of the unknown. If we know that something is there, this is not research. And there is perhaps no, at this moment in time, is so important that experimental project give guidance to theory, because we are in a situation where the standard model cannot explain the various phenomena. There are many theories, you correctly mentioned supersymmetry, which we didn't find at low energy scales, at the scale that we are exploring now. Doesn't mean that it doesn't exist at higher energy scales, and Renaud explained why it's so important. There are many other theories, but we have no clue. And so making a step forward in terms of energy scale and try to get hints will perhaps redirect our thought. I would like also to mention that in any case, the machines that I have mentioned, they all have a big chapter of good work to do. And this is the Higgs boson that has been mentioned by Nigel before. Because the Higgs boson, yes, it has been discovered. However, it's the most mysterious, together with neutrinos, is the most mysterious particle we know about. His quantum number is very special. Nigel mentioned that is the first elementary scalar with spin 0, which also has cosmological implication. But if you look at the standard model, which is a theory that we know very well, we used to say that it has been verified experimentally with very high precision, correct. However, all the problems in the standard model arise from the Higgs boson. If you look at the theory, we call it Lagrangian in our jargon in physics. All the problems comes from the terms that involve the Higgs boson. We don't understand the mass of the Higgs boson. We don't understand the vacuum stability. We don't know if our universe is stable or metastable. We don't know the family problems that Laura mentioned and the flavors, why there are 3 families. So the Higgs boson is a preferential door into new physics. So studying it with the highest possible precision is a must. And this future collider will do so. So already that justifies them. And of course, they will also give us great hints about the other question, because also excluding theoretical scenarios, redirecting our thoughts is as important as new discovery, as measurements, precise measurements are very, very, very important. Look at the measurement that, for instance, satellites like WMAP at Planck have made of the universe. They didn't discover anything, but they measured the composition of the universe in terms of dark matter, dark energy, and many other understanding of our universe that really revolutionize our understanding of the cosmos. So we should be careful not to think that a success in science is just a discovery. Of course, discovery is very glamorous, it's very nice. If Laura could report evidence of dark matter scattering of nuclei, she would be very happy. But if she doesn't find it, the measurement that her experiment will do and the exclusion and that their experiments will provide are equally important.
Yeah. I'm just going to make one comment here while you're getting ready. So I have a friend who's a theoretical physicist, and he guaranteed me that new physics was going to be found for the very reason that Fabiola talked about, is that we think we understand how to calculate the mass of the Higgs boson, but we don't. It doesn't work. So you insert certain things that you need to know that you think you will find in the future, new particles that you would find in the future, to make that calculation work. And you say, there, I know there has to be new physics. And I would say the vast majority of our field before the LHC turned on were, I'll say 90% sure that this new physics was going to show up. So we're even more puzzled now that it's not there day one. I had a friend who said, you'll find it in 3 weeks. And I thought, yeah, sure. So that was kind of the attitude we went in with. And when you don't find something, then people start getting very creative. And that's why you start talking about new accelerators, new approaches, these kind of things. It's just, it drives the field forward when you don't find what you expect. It's a very exciting time in that sense.
Yeah, and I'd also like to say that, you know, one of the exciting parts of doing science is this exploration of the unknown. And I'd like to give a historical example that goes back to neutrinos. When late 60s, 70s, the first neutrino detectors were built actually to look for neutrinos coming from our sun. As you know, our sun is a giant fusion reactor that produces lots of neutrinos. Basically 65 billions go through you per second, through every centimeter square of you per second, just from the sun. But anyway, back then experiments were built to measure these neutrinos, but on the other hand, also to look for something else that we haven't found yet, which is called proton decay. Right? One of the big questions is there some underlying symmetry? Why are protons, the nuclei of hydrogen atoms, why are they stable? Right? So there were these big experiments that were built to see, maybe to discover proton decay. And you know, they haven't seen, so far we have only lower limits on the what we call half-life or the lifetime of the proton. But what they have seen were, what they saw are these solar neutrinos, but at rates, for example, that were lower than predicted, right? So for a long time, the question was, well, maybe there was a problem with the experiments, maybe the sun, our model of the sun doesn't quite work so well, and so on. But in the end, they revealed fundamental properties of neutrinos, namely that from the sun, on their way from the sun to the earth, they actually change what we say flavor. We said that neutrinos, like the other particles, come in 3 families, so they actually, it's a quantum mechanical effect where they transmute from one flavor to the other, and that can only happen if neutrinos have mass. If they're massless, this quantum mechanical effect is simply not there. Right? So experiments that were built to look for proton decay made this other discovery that actually the sun does work in the way we know, we think, you know, that it works, but that neutrinos actually have mass, and that was something that was not predicted by the standard model. So my point was that sometimes you also have to be prepared maybe to make other discoveries that you were not looking for.
Yeah, that's, of course, a really wonderful example. I'd like to get back to the facilities, but let's take these questions first.
Hi, sorry. I'm Rob. I'm a freelance journalist from the UK. I was just wondering, Richard Feynman said that if all scientific endeavour ceased, the one piece of information he'd pass to a new civilization or a new society would be the atomic model. If you could do something similar, but instead pose a question, a research question for a new civilization or a new society to essentially kickstart particle physics all over again for them, what would that one research question be?
Okay, so I guess if I can start, I would ask the question whether our universe is the only one, which probably is not very likely, or whether we live in what we call a multiverse, right? Whether there are more, so these are mathematically predicted, but at this point we have no way of probing this fact experimentally, whether our universe is the only one or whether we live in what we call a multiverse, right? Because then if that would be the case, for example, then some of the questions that we are trying to tackle, like why is the value of this dark energy what it is, that becomes just an environmental parameter, right? So why is the distance from the sun to the earth what it is not a fundamental parameter of any theory, it's just, so you have lots of suns, lots of stars in the Milky Way, right? And you have many, many planets and so on. So that's not a really fundamental question. So what I'm saying is that in that case, some of the questions that we think now are fundamental wouldn't be so, but would be just one parameter in a very, very large ensemble of possible parameters.
Okay, thank you.
Okay, so my name is Hannah. I'm a physics journalist. And my question would be, we know that in the future we will need a lot of creativity in this field because progress is pretty, let's say, slow. I mean, I know that you won't like that, but I think it's not like biology where there is so much happening at the time, but it needs a long breath, right? So these are all projects that take maybe 50 years or 100 years. So how do you teach your students to have this grit, to kind of not let go? How do you make sure that the new generation of physicists can take over from you and follow this, that they don't just drop out?
Maybe one thing to have in mind is that so we've been discussing large facility, large project, but there are many other smaller size projects that are going on, and also that can get result in a year or something, or a few months sometimes. So so those are happening at the same time, and so students can get from one project to another. Work on a long time one for some time, or a very large one for some time, and then get back into a smaller project. So I think it's not just that they don't do anything for 20 years and then they come when the detector is ready to operate. And yeah, that will be my contribution.
I can perhaps complement this. With my own experience, I've been a young postdoc in Atlas, one of the 4 big experiments at the Large Hadron Collider. And when I started, the Large Hadron Collider did not exist. Atlas did not exist. So we are at the level of prototyping and first ideas for the physics reach and the physics potential. And then I've been in the experiment all the way up to, until, and after the discovery of the Higgs boson. I can tell you that there was no single day where I was bored, because such a big project goes through different phases. There is a phase of prototyping where you have to be creative to invent detectors that have to face unprecedented challenges, and then you have to build these detectors and understand how to, then you have to design the experiments, and those are very interesting because you have to meet the physics goals of the experiment. Then you have to confront yourself with the engineers, because of course physicists are always very ambitious and engineers are more realistic when it comes to the design of the detectors. Then you go to the construction, and then to the commission, and then to the first data, and then to the possible discovery or a huge amount of nice physics. And then when you are at the end, when you are there at the in the physics exploitation area, then the project is going to be upgraded. So you need to change your detector technologies to face the new challenges, to develop new cutting-edge instruments. And then perhaps in parallel, the new facility is being proposed, and so, I mean, it's not really, it's a long-term, of course, project, but it's never boring, and it's always stimulating for the young people. Also because these big projects have a large amount of different technologies. So when you work in an experiment like Atlas or CMS, for instance, and even if you work on a part of the experiment, for instance, I've been involved in the electromagnetic calorimeter, but we are exposed every day to 10 other technologies. And if you work on the search for the Higgs boson, you are exposed to 100 different analysis studies and 100 different physics studies. So it's really a very stimulating environment. So okay, that's my contribution to it.
Yeah, I would just say that it seems to me we've just gone through a very exciting period of discovery. So I can just think of a few. So the picture of the black hole on the front page of the newspaper. Nobody's ever seen a black hole before. It just, by the way, it just looks like a black circle on a newspaper. There was the discovery of black holes merging. There was the discovery of neutron stars, and then this whole idea of multi-messenger astronomy has now emerged, where the next thing you'll see is neutrinos being detected from neutron stars merging, and so it's opening up, new questions. It's opening up new fields at the same time. So that's on a big scale, but then on the smaller scale, at least in the United States, and I think elsewhere in the world, the big push for understanding quantum information science has accelerated tremendously in the last 2 or 3 years, where governments around the world have all of a sudden got interested in this for the technology reasons. But from the scientific standpoint, one example I'll give you is now people are looking at detectors where Laura mentioned dark matter interacting with nuclei. People are looking at dark matter interacting with electrons now. It's a much harder problem to solve. But with these quantum detectors, you can start to do that. And so I see things almost accelerating in many ways. The other example I would give you is the polarization of the cosmic microwave background, which is now a very interesting field that's going from smaller experiments where graduate students have built them to large-scale facilities that are in different continents, and you're connecting the data together and so on.
I think the question also relates to the connection between the big discoveries and the everyday work life of physicists, and maybe you want to comment on that.
Yeah, I mean, so first, hello, Hannah. Nice to see you again. Maybe from the more pragmatic point of view, and if I can comment now for the astroparticle physics experiments, yes, when I started in this field, again, long time ago, we had tabletop experiments, right? And now they're getting bigger and bigger, but I would say we always go in steps. We never extrapolate to crazy new dimensions. So what I'm saying is, I have a lot of students in my lab. On the one hand side, when we build the next bigger detector, we still have data from the one, let's say, we just took apart, right? And that analysis of that data, that takes a few years. So the students, they analyze the data from the previous detector, while at the same time they develop the technology for the next generation detector. And that also means, at least in our case, that they operate small detectors in our lab. That's a lot of fun because, as it has been said here, you don't just simply scale up your previous experiment. You always have to build a much better version of it with much lower background and all of that. So, and that's not trivial. That also takes a few years. So that's why I totally agree with Fabiola that they don't get bored. They always have some data to analyze. They always have some new detector to develop. Yeah. So this is how you go day by day. So day by day, you're not in your lab, you're not driven. Of course, you always have the big question in mind. In our case, let's say, are neutrinos Majorana particles, or what is the dark matter made of? But on a day-to-day basis, you have to solve a lot of much, much smaller and much, much more mundane questions, but that are totally relevant, right, to build your detector.
We sort of touched earlier on the future big experiments, and I'd like to hear what you have to say both about sort of how to choose which way to go, but also about global participation and collaboration.
So first of all, the choice will be based on scientific arguments. So when you build a facilities, small or big, when you embark into an experiment, the motivation comes from physics. So what is the physics reach? What are the questions that this facility will allow us to address, or what kind of progress we will do? As we mentioned before, it can be in terms of discoveries, it can be in terms of excluding some unfounded thoughts and redirecting our thinking toward more promising venues and directions. It can be measuring with very high precision the universe through gravitational waves rather than the Higgs boson to understand if there is physics beyond the standard model and where it sits. So physics is the first thing. And then, of course, we will have to confront on realities, meaning financial cost, meaning also the human resources, because of course the community of particle physics across the world is not infinite. So we have to make sure that we are able to big facilities or 3 big facilities are affordable, and we cannot afford more than those. So I think that now we have a big facility in the US with the long baseline neutrino facility at Fermilab and in South Dakota. Then there may be a facility in Asia and one at CERN, but not more than that in terms of big experiments and accelerator-based experiments. And then, as I said before, we will have to work globally. Now, until now, actually, the field has demonstrated to be pretty good in this global endeavor. The Large Hadron Collider perhaps is not a global facility because it's mostly run by CERN, but it has a very strong international participations. Today, if you look at the population of the CERN users, these are the physicists from all over the world that work at CERN. We have some 18,000 people, more than 110 different nationalities, and more than about 40% of them come from non-member state countries, from US, from Japan, from Russia. We used to say that CERN is the second largest US laboratory in the world after Fermilab, because we have 2,000 US scientists. So
I can say the Department of Energy views you as their second favorite lab director too.
Thank you so much, also. You made my day. So we are used to. And actually, I must say, Toni, that very often particle physics is taken as an example for other disciplines or also for other fields of society. The UN, the United Nations, came to us a couple of times to tell us, ask us, how do you work? How is it possible that in the big endeavors in particle physics, in this big collaboration in the US, in Europe, in Japan, you are able to get together people from all over the world, from privileged countries, from developing countries, all kinds of nationalities, and work together toward a common goal? And for me, the answer is our common passion for what we do. Of course, so we are passionate about science, and this is a very, very, very strong glue. So I think that will be the same for the next facility.
Maybe adding a bit on that, what people maybe don't know very well is the fact that the whole process of discussing the physics is done at the labs level, at the country level, but also at the international level in a very well-organized process. So, researchers, they discuss, and students, and everyone is invited to give his opinion. So this is organized every so many years, so that out of that to get a very strong, important and well discussed direction, the physics direction for the future. And I think that's the basic of this process.
Well, right. So I think I can confirm this also for the field. Speaking now for the field of astroparticle physics, I think it was mentioned here, APEC, this consortium, and even though our experiments are maybe not quite at the scale of CERN and the next future colliders, they're, as it was mentioned here, they're also getting bigger. So also we are discussing within Europe. Within this APEC, and there is this General Assembly where there are representatives from all the countries in APEC. So we are discussing, we are setting priorities, because obviously we do have to work all together to build these future larger experiments for either dark matter physics or neutrino physics and so on. And then, again, we discussed this also in a global context. So with, we discussed with our colleagues in US, in Japan, in China, Korea, and so on. So we are trying to put our efforts together, because when we get bigger, there will be only a few of these global experiments. But there's already, as Fabiola mentioned, there's already a lot of experience in joining forces.
Yeah, I'll just make a comment here that I think when you start to put an experiment together, you think about, and our field is interconnected in the sense that most people know most people. It's large, but it's not infinitely large. You ask yourself, who do I want to be working with on my experiment that knows the most in the area that I need help with? And so that inevitably forces you to go all around the world. You don't care where it is. You just want to get the best people with the best technology working on your experiment. And everybody has the same strategy. And so when you approach them, they say, yeah, we'd like to work on this because we think this will be the best place to work on it. And I think that's what drives our field. If you want to look at the high energy frontier, you're obviously going to go to CERN and look at colliding beams at CERN, for example. And clearly the world has decided that's what we want to do, because that's where most people work. But that's also true on smaller experiments as well. You always want to bring the best people together, and they're never in the same location.
Fabiola, did you want to add something?
Well, I just wanted to add perhaps that also science in this moment in time, in particular big science, has also some kind of social and goal and ambition, in the sense that our world is more and more fractured. There are all kinds of forces pulling it apart. And science still remains a domain where people work together across borders. Science has no passport, no religion, no tradition, no culture. We all work together, no gender, and we all work together, animated by the same passion. So I think that is also a kind of message, that positive message that science can give to humanity in this delicate moment.
So how does it work with, say, neutrinos in US and Japan, some similar-ish experiments, and then also with choosing next large accelerators with China and Europe looking at similar designs? Is this more competition or more collaboration?
I'll give the example of neutrinos in Japan and the United States. So I would say that scientists are fairly passionate about what they want to do. They think their approach is the right approach. So if you have two groups that think there's two different approaches, they're going to want to do their own thing. But there's always a lot of common problems. And so if you're smart, you're going to work together on the common problems. So the Japanese work with us in our program, and we'll work with them in their program, and that's how the field progresses.
Maybe on neutrinos as well. So there are, Japan and US are using very, very different techniques to this problem we are trying to solve is a very complicated problem. So it's always good to get, different view. And on this aspect also, there are, neutrino experiments that are based on detecting neutrinos produced by reactors. Also, neutrinos produced by the atmospheric neutrinos or cosmic neutrinos, and those are also very large detectors. Experiments that are addressing the same question in a very different way. And I think it's important to understand these very complicated problems that people work using different tools. Yeah.
What about the accelerators?
So about the accelerators, of course, there is both competition and collaboration. Clearly, healthy competition where people, talk to each other, is also a kind of fuel for science, because it pushes us to be more creative, to have new ideas, and for instance, we work together with the Chinese in that we attend each other workshops. CERN physicists sit on the International Advisory Committee to the Chinese collider. So we are working together. There is a little bit of competition, of course, because if Europe decides that, for instance, a 100-kilometer ring is the way to go, then of course Europe will do its best to get the facility at CERN. That's obvious. But then, of course, there will be collaboration across borders in order to be able to, to work on one of these facilities, and we will see how to involve the Chinese in our facility. On the other hand, if the Chinese go ahead and Europe does something else, we will collaborate with them, of course.
Let's take a few more questions that we have time for.
Yeah. Dominique Leglu, I'm the director of two French magazines, La Recherche and Science et Avenir, and I want to go on with this discussion, wondering whether what Fabiola said and expressed, which has been going on since the Second World War, whether she's sure, and the other panelists are sure, that it will go on. What I mean is, don't you think now that with all these questions about technology transfer, especially between US and China, might impair all the work of the fundamental scientists in particle physics on these big machines which really need forefront technologies? Are you sure that what's been said and repeated for decades will go on? Are we not in a new era?
So I'm not so sure if I understand exactly what you mean by that. So first of all, the technologies, these new machines will require new technologies. Europe, at the moment, has, together with our US partner in particular, has some leadership in the technology. We don't have yet the technologies for the future big collider, but we have a path to get to there. We know what are the next steps, and we are doing, as Laura was saying before, R&D work, prototyping toward the goal. So I think in Europe, with the help of the US, because we are a strong partner on, for instance, superconducting magnets, etc., we will be able to build this collider. So that's for the technologies. And let me also mention that this technology, of course, will benefit society at large, as the current technologies from particle physics and other science research, fundamental research, benefit society. Concerning the relation with China, I think we will continue to work with them. Clearly, in Europe, in the US, but at CERN, one of our fundamental mission is open science. So for us, science must be available to everybody. What does it mean? It means that we publish our scientific articles in open access journals. It means that we develop open source software. It means we develop open source hardware. It means that our data are available to everybody. You know very well that the World Wide Web was made available in 1993 to everyone to use and develop. So this is the way we work. And of course, we hope that the partners that work with us also respect this principle of openness.
Please.
Hello, thank you very much. My name is Katrin Kapretz. I'm also working as a science journalist for Swiss radio station. I wanted to ask, considering the Chinese plans for a big circle collider, is CERN maybe at the risk to lose its leading position in that field? Because, I mean, what's made CERN that outstanding institution that it is today is that it is a big collaboration in between different countries. And now there is one big country which is not especially known for long democratic processes in terms of big projects that it wants to realize. So I heard people say if China decides to dig a 100-kilometer tunnel, then it will simply do it. And I think for CERN, getting there, in case the decision is taken, will be much more complicated and take much more time. So yeah, there is competition in the field, and I think it's a very fast and powerful competition.
Yeah, I'd just make a technology comment here. I think China's capable of building a tunnel. They're not capable of building the machine. The technology that's gone into building the LHC is very, very sophisticated, and I'm guessing that it takes 1 to 2 decades to develop that technology. And so, you know, the discussion that takes place, I'll say at the director level, is that we're, I'll say, excited that China wants to get engaged because, as Fabiola said earlier, that's a big country and they're influential, and we would like them to be interested in our physics. But they have to participate in the rest of the world. I think perhaps you were alluding to that. And we will put enough pressure on them that they need to start to invest in science outside of their own country so that they're a player like everybody else, and then physics really is global. But at the moment, I think it's fair to say that Chinese physicists want it to be global, but their government has yet to demonstrate that's the case.
I fully echo what Nigel said. Just want to add that thank you for the very good question. Yes, there is a risk. However, so first of all, we have to decide what kind of facility we want to have in Europe. We are not just going to build a collider like that just for the sake of it or just for the sake of competition. We do it if there are strong physics motivation. This is the first thing. And now Europe in this moment, as you know, is in the phase of developing, updating our roadmap. This is called European Strategy for Particle Physics, and the deliberation are expected in May 2020. So at that point, if the European community will decide that, for instance, a 100-kilometer collider tunnel with a possible plus minus and proton-proton, ion-ion collision is the way to go, then I can assure you that we will fight to have it in Europe. And of course, our strength, as Nigel mentioned, is the fact that, as mentioned before to the previous question, we master the technology today, and we have a roadmap toward it. And second, that we have the expert, the accelerator expert, the machine expert are mainly in Europe and in the US.
Thank you. Well, we're over time. Thanks everybody for your questions, and thank you all for participating. And I think we could talk for much longer, but we don't have the time. So thanks so much.
Thank you.